Hello everyone, welcome to our channel. Let's start our discussion and solve physical science question paper of SET 2024 for Northeast region. The answer key is available in the official website. You can check there. But in this video, we will go through each question in detail. So that will help you prepare thoroughly for your upcoming exams. There are total 100 questions. But for today, in this video, we will solve the first 20 questions. Okay, let's start. Question number 1. A periodic function f of t is described as f of t equals to I naught sin omega t for this period 0 to pi and f of t equals to I naught sin omega t plus pi for this period pi to 2 pi. The Fourier analysis of this function contains odd harmonics, even harmonics or a dissenter. We have to find. Okay. So here you don't have to calculate any Fourier series, but if you recall the Fourier series, for a full-length Fourier series, we write the Fourier series f of t as a naught by 2 plus summation n equals to 1 to infinity a n cos nt plus summation n equals to 1 to infinity bn sin nt. Okay. Now this can be written as a naught by 2 plus a1 cos t plus a2 cos 2t plus a3 cos 3t plus other terms plus b1 sin t plus b2 sin 2t plus b3 sin 3t plus all other terms. Now this can also be rearranged as a naught by 2 plus a1 cos t plus b1 sin t plus a2 cos 2t plus b2 sin 2t plus a3 cos 3t plus b3 sin 3t plus all other terms. Here this a naught by 2 is called the DC term. This a1 cos t plus b1 sin t is the fundamental or first harmonic. This a2 cos 2t plus b2 sin 2t is the second harmonic, and this term a3 cos 3t plus b3 sin 3t is the third harmonic. Now, if in your Fourier series there is term only a naught by 2 plus this fundamental and third harmonic, that is a1 cos t plus b1 sin t plus a3 cos 3t plus b3 sin 3t, similarly a5 cos 5t plus b5 sin 5t, then this expression will be considered as DC term plus odd harmonics. Now, if this Fourier series expansion contains a naught by 2 plus this even like second harmonic a2 cos 2t plus b2 sin 2t plus a4 cos 40 plus b4 sin 40, then this will be considered as the Fourier series contains even harmonics. Okay. Now we will see for the given function what will be the result of this Fourier series. Okay. Now if you will see the function is given as f of t equals to I naught sin omega t for 0 to pi and f of t equals to I naught sin omega t plus pi for period pi to 2 pi. And you should remember one thing, if a function f of t plus pi equals to minus f of t, if a function satisfies this condition, then its Fourier series will contain odd harmonics. with DC term. Okay, with DC term. Now, if a function satisfy a relation f p plus phi equals to f of p, then the Fourier series will contain DC term plus all even harmonics. Okay, now you can check for this function. Okay, f of t equals to I naught sine omega t for 0 to pi. Now, if we will draw like this is 0. Now, let this pi 3 pi by 2. Now, this is 2 pi. So, for 0 to pi, it is like this sine omega t. Now, if you calculate at pi, it is here. At 3 pi by 2, the function is this. That means f of t at 3 pi by 2. Okay, it is I naught sine pi plus 3 pi by 2, that is high pi by 2, or that is I naught sine 2 pi plus pi by 2, or I naught sine pi by 2, or that is I naught. Okay, so at 3 pi by 2 it will be here, and at 2 pi it will be sine 3 pi, that is 0. So the function will vary as this. So you can see this function satisfy this condition that f of t plus pi equals to f of t. Here from the graph we can see this is a function with period pi. So the Fourier series for this function will contain DC term and all even harmonics. So your correct option will be option B, a DC term and all even harmonics. Question number 2. The general form of the linear differential equation of second order is P, Q are constants and R is a function of X or constant. And we know this general form of linear differential equation of second order is d square y by dx square plus p di by dx plus qy equals to r. So your correct option is option A. Okay, so let me write from the first order linear differential equation. First order linear differential equation, and it is given by di by dx plus py equals to q. Okay, so here p and q are either function of x or their constants. Okay, so you should remember this general form also. This is first order linear differential equation, and if you see its solution is given by, or it's solved with the integrating factor, and integrating factor is given by exponential integral of px dx, and its solution is y times integrating factor equals to integral integrating factor multiplied with q of x dx plus c. Okay. Similarly, linear differential equation second order. Okay, it will be d square y by dx square plus p dy by dx plus qy equals to 0. If it is 0, then it will be homogeneous, and if d square y by dx square plus p dy by dx plus qy equals to r, then this will be non-homogeneous second order linear differential equation. Okay. 3. The number of degrees of freedom for a free rigid body in space is 6. So your correct option is option C. Similarly, you should remember the number of degrees of freedom for a rigid body if one of its point, if one point is fixed, then in that case the degree of freedom will be 3. Okay. Next, if the rigid body rotates about a fixed axis of rotation, okay, fixed axis, then in that case, degree of freedom for the rigid body will be 1. Question number 4. Which of the following statements is correct? Okay. So let us read all the options. Option A, the Lagrangian equations of motion are first order differential equation. Okay, now let us see the Lagrangian equation. We know the Lagrangian equation is expressed as d by dt of del L by del Q dot minus del L by del Q equals to 0. And this is a second order equation. Okay, now next option. D'Alembert's principle gives a first order differential equation of motion. We know this D'Alembert's principle gives the Lagrangian equations of motions, which is a second order differential equation. Okay. Now, option C, Hamiltonian equations of motion are first order differential equation. Yes, these are first order differential equations because Hamiltonian equations of motions are given as Q k dot equals to del H by del Pk and Pk dot equals to minus del H by del Qk. So these are first order differential equation. Okay. So your correct option is option C. Hamiltonian equation of motion are first order differential equation. 5. The Lagrangian of a relativistic particle is. We know the Lagrangian of relativistic particle is given by L equals to minus m naught c square root under 1 minus v square by c square minus ux. So your correct option is option C. Similarly, you should remember the Hamiltonian of a relativistic particle, and that is given by square root under p square c square plus m naught square c4 plus u of x. Actually, you can derive that Lagrangian uh, from this Hamiltonian, and for that you have to use the equation L equals to p q dot minus h. Okay, and to derive this q dot, you have to use the Hamiltonian equation, that is del h by del p. Okay, now if it asks about the Lagrangian of a relativistic free particle, for a relativistic particle, Lagrangian is minus m naught square root under 1 minus v square by c square minus u of x. But if it asks about the free particle, then the potential will be 0. So Lagrangian, it will be L. L will be minus m naught c square root under 1 minus v square by c square. Next, Lagrangian of a charged particle in electromagnetic field. Okay, you should also remember that Lagrangian is given as P minus V, and the potential for a charged particle in electromagnetic field is given as Q phi minus Q A dot V, where phi is the scalar potential and A is the vector potential. So the Lagrangian will be T is the kinetic energy, that is half mv square minus Q phi plus Q A dot V. Question number 6. Which statement is not true in the following? Okay, so read it carefully. This is asking about which is not true, that means which is not correct. Okay, so let us read all the options. For a test charge placed at infinity, the electric field will be 0. Okay, see, electric field magnitude is given by k q by r square for a charged particle q at a distance r. Now, if the distance r is infinite, then the E will definitely tends to 0. Okay, so this option A is correct. Okay, so next, come to the option C. Gauss law cannot be used to find permittivity. This is also correct because permittivity for a object is constant. Okay, so Gauss law cannot be used to find permittivity. Next, charge in space is the example of spherical system. This is also correct. But if you see, the Gaussian surface is tangential. But sometimes the Gaussian surface can be normal also. Okay, so this option here is not correct. Okay, so your correct option is option B. Number 7. The modes of propagation supported by a rectangular waveguide is only TM and TE modes. So your correct option is option B. Here, one more important question is also asked, that is about the dominant mode of propagation. Okay, and you should remember for TE mode, the dominant mode is TE10. Dominant mode means the mode of propagation with the lowest cutoff frequency. And for TM, the dominant mode is TM11. Okay. Number 8. In Fermi's golden rule, the transition rate is proportional to, it is proportional to the square of the matrix element of the perturbing potential. Okay, so your correct option will be option A. You should remember this transition rate is independent of time, independent of time, and it depends on the strength of the coupling between the initial and final state of the system, that is the square of the matrix element of the perturbing potential. Okay, and if you see its mathematical expression, it is given by lambda if equals to 2 pi by h cot mi mod square rho, and this represents the matrix element of the interaction, and this is density of state. Question number 9. The Hamiltonian of an electron in hydrogen atom is h equals to p square by 2m minus e square by r. The wave function psi denotes the ground state with this inner product equals to 1. That means the normalization condition psi is normalized. Now, which of the following option is correct? Okay, so let us check with the all the options. Option A, psi is an eigenstate of p square by 2m. And we know for any wave function to be an eigenstate of an operator, it should satisfy the equation, that is, let for an operator A, psi should a real constant c times psi. If psi is an eigenstate of A, then it should satisfy this equation. So let us check for psi for the operator p square by 2m. Okay, so p square by 2m psi. Now you can write p square by 2m minus h square by 2m del square psi. And h psi is ground state of hydrogen atom, and we know psi will be 1 by square root under pi a naught q exponential minus r by a naught. Okay, so here it will be minus h cot square by 2m del square this 1 by square root under pi a naught q exponential minus r by a naught. So to calculate this, you have to express this Laplacian in terms of spherical polar coordinate r theta phi, because the wave function is in terms of r. Okay, so minus h cot square by 2m, and the Laplacian in terms of spherical coordinate will be 1 by r square del by del r square del by del r is psi 1 by square root under pi a naught q exponential minus r by a naught. Okay, so I am leaving this calculation for you. You can calculate this simple derivative with this wave function, and you will see this will not satisfy the eigenvalue equation. So we can say the psi here is not an eigenfunction of phi square by 2m. Now coming to the option B, the expectation value of r is 0. So let us calculate this. Option B, we have to find the expectation value of r in this ground state. Okay, so here we can write 0 to infinite psi star r psi dr, or we have 1 by pi a naught q 0 to infinite r exponential minus 2r by a naught dr. Again, this says you will get some finite value, and this is not equals to 0. So option B is also not correct. Similarly, in option C, it is asking about the expectation value of 1 by r in this wave function psi. Again, you can calculate this, and this is not equal to infinite. Okay, so now going to the option D, the expectation value of the total energy in the ground state is negative, and we know this energy is negative for ground state. So option D is correct. Question number 10. The ground state energy of the electron in the hydrogen atom is, we know the energy of electron in different states of hydrogen atom is given by a general formula, that is En equals to minus 13.6 electron volt divided by n square. And for ground state n equals to 1, so the energy in the ground state will be minus 13.6 electron volt. So your correct option is option B. But remember, this is for hydrogen atom. If it asks you about hydrogen-like atom, then the general formula will be En equals to minus 13.6 electron volt Z square by n square. Similarly, you should remember about the velocity and radius of electron in hydrogen atom and hydrogen-like atoms. Like for radius of electron in nth orbit is given by Rn equals to 0.53 Armstrong n square by Z. This is for hydrogen like atom. For hydrogen, it will be Z equal to 1, so it will be 0.53 Armstrong n square. For hydrogen atom, Rn will be 0.53 Armstrong n square. So for ground state, n will be 1. So in the ground state, radius will be 0.53 Armstrong. Similarly, you should remember for velocity in n orbit, it will be 2.18 into 10 to the power 6 meter by second z by n. And for first orbit, it will be 2.18 into 10 to the power 6 meter by second in hydrogen atom. Okay. One more concept here you should remember, that is fine structure constant alpha, and it is defined as ratio of v1 by c, that is speed of electron in the first orbit divided by speed of light, and its value is given by 1 by 137. That is your fine structure constant. Question number 11. For a photon gas, the distribution function is given by, we know for fermions, for bosons, there are different distribution functions. So let us write those distribution function first. That is, for fermions, the distribution function f of e is given by 1 by exponential e by kt plus 1. Okay, k is the Boltzmann constant. Similarly, for bosons, the distribution function is given by 1 by exponential epsilon by kt minus 1. Okay, and for the Maxwell Boltzmann distribution function is given by 1 by exponential epsilon by k t. Okay, and here in the question it is asking for the photon gas, and we know photon is a boson. Okay, so for photon the distribution function will be f of e equals to 1 by exponential e by kt minus 1. So your correct option is option D. Question number 12. Two containers are filled with diatomic hydrogen gas and diatomic oxygen gas. The gases have the same temperature. Compare the average speed of the hydrogen molecules to the average speed of oxygen molecule. Okay, so to solve this question, you should remember the average speed for the gas molecule, and it is given by square root under 8 k t by pi m. So if you see, according to the questions, the both the gas molecules, that is hydrogen and oxygen gas, both are at the same temperature. So according to this formula, so 8 constant, k constant, t constant, pi constant. So this average speed will depend only on their molecular mass. Okay, so we have to find the average speed of hydrogen atom to average speed of oxygen. So put the formula. Now it will be mass of oxygen by mass of hydrogen. So it will be 16 square root under 16 by square root under 1. So it will be 4 by 1. So your correct option will be option D. Similarly, there are two more formulas you should remember. One that is for RMS speed, and it is given by square root under 3 kt by m. And the most probable speed is given by square root under 2 kt by m. Question number 13. The combined form of first and second law of thermodynamics is. From first law, we know that the heat given to a system is equals to change in internal energy of the system plus work done by the system, or that can be written as du plus p dv. And from second law, we know dq equals to p ds. So by combining, we can write this expression as p ds equals to du plus p dv. So here your correct option is option A. Question number 14. In television broadcasting, which of the following modulation techniques are used for picture and sound? That is frequency modulation and amplitude modulation. Frequency modulation used for audio signal and amplitude modulation is used for video transmission. So your correct option is option C. Question number 15. An amplitude modulated signal with 100% modulation will have a ratio of total sideband power to carrier power equal to. So for this amplitude modulation, you should remember a very important formula, that is Pt equals to Pc times 1 plus k square by 2, where Pt is the total transmitted power and Pc is the carrier power. And here K represents the modulation index. For K equals to 0, no modulation. For K equals to 1, 100% modulation, and K greater than 1, over modulation. Okay, so here it is given that 100% modulation. Okay, so Pt will be equals to Pc 1 plus 1 square by 2, so that will be 1 plus 1 by 2. So Pt by Pc will be 3 by. Question number 16. In the circuit below, two identical transistors A and B have VBE 0.7 volt and the battery voltage 5 volt. The current passing through the transistor B is. Okay. So if you see the current flowing through here will be same current will be here and the same current will be going through this. So if you can find this current I flowing through this 100 ohm resistor, it will be the same current through the transistor B. Okay, so now let us apply the KVL in this loop. Here we have a VBE that is 0.7 volt. Okay, so applying KVL in this loop, we are having minus from here. I'm starting. So minus 5 volt plus I times 100 ohm, I times 100 ohm. See, current here will be divided into three parts. One will be IC for this transistor A, one will be for IB base current for transistor A and for base current of transistor B. Now going in this loop, I into 100 ohm, then there is no RB, then directly with this VBE that is plus 0.7 volt equals to 0. Okay, so from here I equals to 5 minus 0.7 that is 4.3 by 100, that is 43 milliampere. Okay, so this same current will be flow through this transistor B. So your correct option is option C. Question number 17. Which of the following semiconductor diodes is not a differential negative resistance device? See, here it is asking about the differential negative resistance device. Resistance generally we define as V by I. But here we have to define differential resistance, and that is given by del V by del I. That is change in voltage divided by change in current. So here all these this tunnel diode, gone diode, IMPATT diode, all are having this negative resistance, differential negative resistance. Okay, but this Geno diode having positive resistance. So your correct option will be option A. This is not a differential negative resistance device because when we increase the current in Geno diode, voltage increases. Number 18. The number of splitting levels of the 2p orbital is. See, this question is from Zeeman effect concept. We know uh, in presence of magnetic field, there is splitting of the spectral lines and that is known as Zeeman effect. And we know the splitting of these spectral lines basically depends on the orbital quantum number, that is your small l. And the splitting is given by formula 2l plus 1. Okay, so here it is asking for 2p orbital, and we know for S, P, D, F, L value is for S it is 0, for P it is 1, for D it is 2, for F it is 3. So it is asking for the P orbital. So here 2 into 1 plus 1, that is 3. So here the splitting level will be 3. So your correct option is option C. Question number 19. Choose the correct answer. Sensitivity of electron spin resonance increases with. If you see, this sensitivity of electron spin resonance increases with decreasing temperature and increasing magnetic field strength. So your correct option is option B. And this sensitivity of ESR basically represents the net absorption. And you should remember this electron spin resonance is also known as electron paramagnetic resonance. Okay, so here your correct option is option B. Question number 20. When a monochromatic radiation of wavelength 4358 Armstrong passes through a certain sample, Stokes radiation is obtained at 4458 Armstrong. The anti-Stokes radiation would be 8. Okay, so this question is from Raman scattering. As we know, Raman scattering is the inelastic scattering of light. And in Raman spectroscopy, we found two lines. One is the Stokes lines. Okay, this is the Rayleigh-Jeans lines, for which the incident wavelength and the scattered wavelength will be same. And we found one is the Stokes lines here, for which the scattered wavelength is greater than the incident wavelength, and anti-Stokes lines for which the wavelength is less than the incident wavelength. Here the shift is defined like the difference between the energy of the incident light and the energy of the scattered light. Okay, we defined energy E equals to h nu or hc by lambda, and there is a term called wave number that is defined as 1 by wavelength. Okay, so we will here we will define the shift in terms of this wave number. Okay, and as we know, here we can see the unit of wavelength is defined as Armstrong, and we know 1 Armstrong equals to 10 to the power minus 10 meter. Okay, for this will be 10 to the power minus 8 centimeter. Okay, we will express this Armstrong in terms of this 10 to the power minus 8 centimeter. Okay, now if you see, as we discuss that this for Stokes line, the wavelength of scatter light is greater than the incident light. So we can write the Raman shift for Stokes line. Raman shift for Stokes line, that is 1 by lambda naught, that is the wavelength of the incident line, 1 by lambda s, wavelength of the Stokes lines. And for anti-Stokes lines, the shift will be 1 by lambda as minus 1 by lambda naught, that is the incident light wavelength. And you should remember, for a fixed given object, the Raman shift will be same for a given object, for a same given object. So here in the question, a monochromatic radiation of wavelength this incident on a fixed sample. The Stokes radiation line is at this wavelength. We have to find the wavelength for the anti-Stokes line. So according to our discussion, this shift will remain same. We are given with lambda naught and lambda s. So from using this lambda naught and lambda s, we can find this shift. Okay, now in the second equation, we will use this value, shift value from here, and we have this given wavelength. So we have to find basically this wavelength for the anti-Stokes line. Okay. Now let us calculate. Okay, so this is our formula to calculate this Raman shift. So from here we are having the incident light wavelength and the Stokes line wavelength. So the shift will be 1 by 4358 Armstrong, okay, minus 1 by 4458 Armstrong. So here we can write 4458 into 4358 100. In place of 1 Armstrong, I can write this value. So it will be into 10 to the power 8 centimeter inverse. Okay. So now this is fixed for this given sample. So we have to find this lambda as. Now I will use del nu naught equals to 1 by lambda as minus 1 by lambda naught. So it will be 1 by lambda as equals to mu naught bar plus 1 by lambda naught. So 1 by lambda as equals to this value 100 by 4458 into 4358 plus 1 by 4358 into 10 to the power 8 centimeter inverse. Okay. So now from here you can calculate this 4458 into 4358. Okay, so it will be 4558 into 10 to the power 8 centimeter inverse. Now from here lambda as equals to 4458 into 4358 divided by 4558 into 10 to the power minus 8 centimeters. So in place of this we will write Armstrong. Now if you calculate this you will find 4262 Armstrong. So option B is your correct option. Okay, let's stop here for now. We will continue from this point in the next video. I hope this session will definitely help you in your exam preparation. And if you found this video very helpful, don't forget to like, share and subscribe to our channel. Thanks for watching and see you in the next one.